beam, plate and a shell, what will happen? So these piezoelectric materials are piezoelectric materials, don't get confused, it is just like a quartz crystal. Quartz, titanium, barium, titanium, many materials are there in the apparatus which acts as piezoelectric materials. Piezoelectric materials were first discovered by Madame Curie. So Madame Curie has observed that there are certain crystals. If you apply force on, if you apply force on those crystals, these crystals will produce electricity. Right? If you apply, suppose if you take this chalk is made of quartz material. If you apply some compression load or if you pull it, it will produce some electricity. Right? It will produce electricity, voltage. It will produce some voltage. So then Madame Curie observed that instead of applying stress, if you give voltage to the structure, what will happen? So once you give voltage to the structure will give mechanical output. So piezoelectric material has got two effects, namely direct effect and converse effect. Direct effect is if you give mechanical input, you will get electrical output. But a converse effect is if you give electrical input, you will get mechanical output. So piezoelectric has got both the effects. If you give mechanical input, you will get electrical output. But if you give electrical input, you will get mechanical output. So if you want electrical output, that can be used as an actuator. If you want a mechanical, if you want an electrical output, it becomes an actuator. If you want it to be, if you want mechanical output and electrical input, then it becomes a sensor. Sensor application. So piezoelectric materials can be used in two ways. They can be either used as an actuator or they can either be used as a sensor application, right? Based on the application. So what a smart structure is? A smart structure is a structure which will have a basic mechanical element like beam, plate and shell. Over the top or bottom or both top and bottom, it will have, in addition to the basic element, a smartness adding element. The smartness adding element is a piezoelectric material. So you can clearly see structures which can sense, diagnose and actuate in order to perform a desired function. Such structures are called smart structures. So what smart structure basically comprise of is, smart structure basically comprise of a basic structural element and elements of smartness adding material which acts as either distributed actuator or distributed sensor. So examples of smartness adding materials are piezoelectric materials, quartz, barium titanate, polyvinylidene fluoride, lead zirconium titanate, shape memory alloys, magneto-rheological fluids, electro-rheological fluids, and magnetostrictive and electrostrictive materials. So in this the first one is piezoelectric material. So what I have already explained what a piezoelectric material is. If you give mechanical input, you will get electrical output. If you give electrical input, you will get mechanical output. So in shape memory alloys, what shape memory alloys is like you have. If you take a paper, you will fold it and throw it, right? So after that, you take the paper and again open all the foldings, and if you iron it, what will happen? The paper will retain its original shape. What is the original shape? Original shape is of a rectangular shape. So what you have done? You have made it into a ball kind of thing, and after that, if you open it and if you iron it, you will retain some part of it. So what is like? So shape memory. So the shape actually remembers its original shape. So the material or structure will remember its original shape. After that, what you do is you compress it and you apply heat to that. If you apply heat to that, the original shape it will remember its original shape and it will come back to its original shape which it was there. So this is used in space applications. You might have seen foldable antennas. Foldable antennas, you see the nose cone of the rocket. The rocket will have antennas which should be subjected to thermal solar radiation based on which it will get supply. So what they do is they will fold it, and at that temperature, due to solar radiation, the heat will be there. So the antenna is deployed. So once it gets deployed, it retains its original shape and size. So that is called shape memory alloy. Shape memory alloy means it remembers its original shape, and when heat is supplied to it, it will come back to its original shape. That is shape memory alloy. Magneto-rheological fluids. So magneto-rheological fluids is you have some magnetic particles. So magnetic particles in slurry, you can say slurry is a mixture of abrasive materials and all. So these materials that are present is magneto materials, and if you supply magnetic field, what will happen? The material which is magnetic will align in one particular direction, north-south direction or south-north direction, depending on the application of magnetic field. So that is called magneto-rheological fluids. Electro-rheological fluids is you have to give electric field. Once you give electric field, it will align in that particular direction. That means these abrasive particles should be of conducting nature. And magnetostrictive and electrostrictive materials. These the earlier two were in fluid. These are in solid particles, right? So these are different smartness adding materials. Based on the applications, we can go for that. So as I explained there, so the piezoelectric material has got a base structure. The base structure is either a beam, plate or a shell, and over at the top and bottom, or only at the top or only at the bottom, you have piezoelectric material. So if you supply voltage, it will give mechanical output. If you supply mechanical input, it will give voltage output. So these are the properties of piezoelectric material. You can give mechanical input. If you give, you will get electric output. If you give electrical input, you will get mechanical output. This effect is called converse effect. This effect is called direct effect. Right? So these are piezoelectric materials. Piezo, as I explained, I am not going to in details. Whatever I have explained verbally, this is put in slides. So where these applications are, where are the applications of these smart structures? Smart structures have got a lot of applications in controlling the aerodynamic flutter. So if you see, sometimes if you have traveled through flight, you might have seen sometimes the aircraft vibrates violently. Then people say the pilot over there says we are experiencing turbulence. Like that they will say, then you will see that the wing will vibrate violently. So if the wing vibrates violently, the tip of the wing will be fluctuating at least 100 mm. 100 mm means 10 centimeters. So 10 centimeter fluctuation will be there. So this fluctuation should be brought to rest very quickly. So that's where if you add a piezoelectric material, piezoelectric material and give since you are getting mechanical input, so the flutter can be mechanical input. So that input is converted into voltage, and this voltage is again given back to the system by using a feedback control system. So by using feedback control, so this way the flutter will be arrested. So this smart structures, these piezoelectric materials are used in efficient active vibration control of flexible structures, control of flutter of wings of an aircraft, teleactuation of robotics. So teleactuation of robotics is very important task. Now, like if you have a problem in your stomach or intestine, what the doctor usually do is he will send the endoscopy down the throat, and this endoscopy has also got a small camera, right? And now using this smart structure technology, by use of this, with camera, the doctor can see which areas it should go, and this endoscopy goes in that particular area, and he can see on the screen, and he can operate minutely with his hand like a joystick. He can operate it, thereby you can allow it. So this actuation, you are giving mechanical input of finger here, that is converted into, you are giving electric voltage to it, so it will be converted into mechanical input at that particular location. That is how the endoscopy is going to the locations where it wants. So this is one more application of teleactuation of robotics. Robotics doesn't mean a huge robot should be there. That is there are micro robots or soft robots also. So endoscopy is best example of a soft robot. And active control of noise inside an automobile. So you can also perform acoustic noise control using this piezoelectric materials. And damage detection of laminated composites. If there is a laminated composite structure, and if there is a damage, that means if there is a delamination between that. So if there is a delamination between that and without delamination, if you apply certain amount of mechanical input, you will get say 5 volts energy. And if there is a delamination, if you apply it, what will happen? There is interlaminar sliding between each of the layers, and you will not get 5 volts output. Rather, you will get some 2 volts or 3 volts. Then you can say that the composite that is having certain damage in it. So monolithic examples of monolithic piezo materials are, as I said, quartz, barium titanate, lead zirconate, and polyvinylidene chloride. So there are certain, everything comes with certain price. So there are certain drawbacks with the use of piezoelectric materials. So to say, for example, if you want to move 1 mm, say for example, if this pen, if pen is made of piezoelectric material, if you want to move this pen 1 mm, then you have to supply 20,000 volts of electric input, then it will move 1 mm. Is it reasonable? No. For moving 1 mm, if you want to supply 20,000 volts of energy, it is meaningless and it is reasonable. That's where monolithic piezoelectric materials are not advised for use in commercial applications. So then we have come across what is called new type of composite material, which is known as piezoelectric composite material. So like composite material, in composite material, what you have? You have a matrix and you have a reinforcement. Reinforcement is a fiber. It can be carbon fiber or glass fiber or e-glass fiber. So these fibers are embedded in matrix to form a structure which is known as composite structures. Here in piezoelectric composite material, instead of regular fiber, we will be using the fiber as fiber made of piezoelectric material. So piezoelectric materials acts as fiber in it. So in that way, what you are doing, you are adding the fibers in this particular fashion or in this particular fashion. Thereby, you are multiplying the voltage based on series connection or parallel connection. So if you want to increase the voltage, you have to put in series. If you want to increase make the voltage constant, parallel connection. So increase the current. So that way, these monolithic piezo materials will be added as fibers, and matrix or epoxy. Epoxy is a matrix. Epoxy will act as a matrix. So this becomes a composite material. Since this is having one or more than one material, it is called a composite material. Hence, this composite material is called a piezoelectric composite material because we are using piezoelectric materials. So after, as I said, these monolithic piezo materials need a lot of control voltage. So in order to take, but if you want to use the piezoelectric material at room temperature, so at room temperature, how much is the maximum control voltage that you can get? 230 to 250. You can supply only that much amount of voltage. So in order to do that, say AMR Bus is a scientist. So here you can see A Bus. A Bus is a scientist. He has come up with a new solution that using only piezoelectric material for smartness adding may not be that much effective. Instead of that, between the piezoelectric material and the base structure like beam, plate or shell, if you put a viscoelastic material, then the output that we want increases manifold. So that has been the basic idea behind development of what is known as active constrained layer damping treatment. So active constrained layer damping treatment is combination of two materials, that is a smartness adding material like a piezoelectric material and as well as viscoelastic material. So what is a viscoelastic material? Viscoelastic material has got both the properties of solid as well as fluid. So for fluid, it follows the Newton's laws of viscosity, and for solids, it follows Newton normal Hooke's law. So And the advantage of viscoelastic active constrained layer damping treatment is it has got both the properties of active and passive. What is passive? Without giving any control voltage also, some of the vibrations it will damp. But if you supply control voltage to it, the vibration and damping will be very quick, right? So these are, so just see how design thinking has evolved. Earlier, although in 1870, 1890, during that time, Madame Curie has invented piezoelectric material. And she has observed that if you give voltage, if you give a mechanical input, we are able to get voltage output. But after that, after 10 years after that invention, people have realized that why not try the other way around? That is, by giving electrical voltage to it, can we get mechanical output? So they have invented the converse effect as well. So once the converse effect has been invented, they were not able to extract or use that particular voltage for any application in real time. So from there, you can clearly see how the system has evolved, and they have reached up to 1995. Up to 1995, they could not extract the potentiality of this piezoelectric material. That's where AMR Buzz has designed that using piezoelectric material with constrained viscoelastic layer, we have observed that wonders can be created in reducing the vibrations of any structure. So the design thinking has evolved from there, and he has come to this particular point. You can clearly see here, this is the work that I have carried out during my PhD. You can clearly see, as you know, if you have if you give free vibe, if you say, for example, if you, this is a table, if you just tap this, what will happen? This table will vibrate, right? So if you record these vibrations, the vibrations will be like this. So according to Newton's first law, every body continues in state of rest or in uniform motion unless acted upon by an external force to change the state of rest or uniform motion. Right? So if I give free vibration, what is free vibration? Just you give initial disturbance and leave it, the system will oscillate. But it will continue, whether it continue to oscillate over a long period of time, no. After some time it will reduce. Why it is reducing? Because there are wind loads and external factors, and there is friction between this, and this material has got certain damping. So after some time, the damping is causing the vibrations to reduce over a period of time. But according to Newton's first law, it should not reduce; it should continue to vibrate, right? So if you give free vibration, the free vibration response will be like this. The damper will reduce the vibration. So this is without damping. Without damping. This is with damping, right? But every material has got internal damping, that is due to friction or any other factors. So without damping, so it will be slightly more than this. Something like this, right? That's why you can clearly see, as I said, every material has got certain amount of damping. If you don't give control voltage to it, but you can see that the damping is always present. So that's why it is not oscillating in continuously oscillating in the same amplitude. The amplitude is reducing after each and every cycle. So these are oscillations very close to it. In that way, it is reducing. This reduction you can see is due to the presence of internal material damping with it, or in this particular case, it is due to passive damping. What is passive damping? You don't supply any voltage to it, that is passive damping. But if you supply the voltage, the red one you can clearly see, the red one damps very quickly compared to the blue ones. Blue ones is without supplying the voltage, the red ones is supplying the voltage, right? So these are the responses that I've caused, I've created for, and you can clearly see voltage that I've put is, voltage limit that I've put is 300 volts, because that much amount of voltage only you can get it at room temperature. You can't take voltage if you supply 1000 voltage for getting small damping, that is meaningless. So whatever the supply you can get in room temperature, room conditions, that much if you are able to extract and get the damping, that will be much better, right? So that's why you can clearly see it has reduced. So the first one, the blue one is the passive damping, where control voltage is not given, and the red one is the damping or reduction in amplitude when control voltage is given. The corresponding control voltage for this is, so for getting the red one, the voltage that needs to be supplied to the system is like this. Similarly, for the case of clamp, this is simply supported condition. That means the plate that we have taken is a simply supported condition plate, and this one is a clamp. Clamp means it is clamped at both the ends. Aluminum or bronze or engineering material. There are several engineering materials, but why we need to go for composite structures? So we go for composite structures because composite structures have high specific strength. High specific strength means without increasing much weight, you can get the similar amount of strength. So that's why we go for composite structures. So as you have seen, I worked on sandwich structure. Why I worked on sandwich structures is sandwich structures have got better ability to withstand in comparison to composite structures. So I will tell you the example of it. So this is a, you can say, you can assume that the cross section is rectangular, right? If I ask you to make a beam with this beam, I want you to make a beam with this remote, then how will you simply support beam? I want you to make with this. So what you will do? You will support like this, right? Usual tendency of human beings would be to support like this. But if you do like this, what will happen? If you apply the load, you will notice that so let's take like this. I will draw. This is a simply supported beam, and you are placing